Last meeting, we were discussing approximation and we stuck with the discussion of value function approximation and finished with getting to the DQN algorithm, which is like a big extension of value function methods that has a lot of bells and whistles attached to it to try to address some deficiencies that can happen when we use approximation. And this meeting, we're going to move on to policy gradient methods, which are covered pretty thoroughly in the Sutton and Bartow book. And there are links here on this slide to some of the material we've previously gone over, these notes, and also recordings of meetings where we discuss that. So I'll put a link to this slide in the video recording too. So when people are looking at this, they can get it. Like this is an example of, these are some of the notes, one of the notes pages we went over for policy gradient. We'll get back to this in a second. First, I wanted to wrap up the discussion of DQN, where throughout this, to evaluate different approaches, we're going to use sort of a grid world example. Like this is an example in the book where there's an agent trying to collect an item here. This is sort of equivalent to like a grid world maze problem where this apple is just like the exit of the maze. So for the purposes of my notes, I'm just going to use a grid world example for this because like this example really is no different from that. This example is extended later with multiple agents and multiple items, and then it becomes a little different. But for this single agent stuff, it's just like a maze basically. So the example we're going to be using, I introduced it last time. It's just this example from that is also used a lot in the Sutton and Bartow book. This maze is, there's like a starting point and a goal. What's being shown here is like an exact solution to the problem, which you can calculate with some tabular solution techniques. So the reason why it's not just straightforward of like heading straight to the goal is because there's like this sort of wind in this maze that tries to blows the agent up. So when it tries to move over, its position sometimes is affected by the wind. So it makes the task a little harder. And instead, it has to learn how to do this sort of wraparound thing where it has to, go over the top of the goal state and then end up getting back to it. So, it's a little more complicated than just the straightforward problem. Actually, in the book, this is really, as straightforward as just, moving straight to where the item is. So it really, like there's no weird obstacles in this to make the problem more difficult. Yeah. So yeah, this is the exact solution. Also, here is the value function for the problem with this discount rate of 0.99, which we're going to use throughout these examples. So yeah, the value function is the tool we use for these types of problems, and for all tabular problems, to calculate the optimal policy, because we just move in the direction of higher value. Right? So once we have the value function, right, like points with lower values are in a worse position, that it'll take longer to reach the goal from those positions, and then higher values are closest to the goal. Like here, the highest value is right here, right under it, because this is the spot you want to be in where you can basically just, select a down move, and the wind in this case will blow you up into the goal position where we don't have a chance of overshooting it or anything. I think there's probably a small chance of overshooting it here or something. Yeah. So for this exact solution, you can see here the value function. Basically, the total number of steps to reach the goal here is like 21 steps. I'm going to go back to this. Yeah, so here, like this line here in my notes, this is just forming that same environment I showed before, where like these are the wind values. That this also makes the environment stochastic. So the wind, like the amount it will displace the agent will actually is not always the same. It has some probability of being 3 different values in this case. So this is a tabular problem. We can just create an exact solution for it, but so you would never really need to use approximation techniques to solve this problem, but we can use it as a nice test case because like we know the exact solution. So when we use approximation techniques, we can easily compare them to the exact solution. So here I have this like little utility that lets me just take this problem where in a tabular problem, we have this, like, in this case, the problem has 70 states. So we have this exhaustive list of states, and we can turn it into an MDP, or a Markov decision process, where all these reinforcement learning problems are in this format. But this is a type of MDP where, in general, we don't need to have a state list. Like that, there is a thing that is a state that gets updated that we have to know what it is and how it gets updated, but there's not a restriction on the state space like there is in this. So here, even though this is a problem that is restricted, I can also treat it like it's unrestricted, and then all the algorithms that are suitable to use with these types of like unrestricted state spaces, then we could apply it to more difficult problems later. Okay, so we have the grid world, and then just I mentioned like it's a pretty small problem. Like the grid, what's being shown here is the exact value function, but as a heat map instead of what I showed before, where here's it should just map onto this perfectly. Just here's like the numerical values, and then this is the heat map solution. But you can kind of see the shape of it here. This doesn't have a value that's filled in because this is the terminal state of the goal. So, its value is always 0, but I'm excluding it because if I put a 0 here, it's going to screw up the legend of this heat map. So it's just the goal. And, this problem, it's pretty easy to solve. Here I'm using, we can always use something like value iteration to solve an exact problem like this. But if we look at, here's like the random performance of an agent in this environment, and we can see that actually it's probably worse than you might imagine. If you just move randomly, it actually takes an average of almost 4,000 steps to reach the goal. And the maximum observed here, I took, I think there's, this was evaluated over some number of trials. I don't remember exactly how many, but out of all the trials I computed, the maximum was actually 31,000 steps. I put a cap here so it doesn't like run forever, but actually the maximum I observed is less than the cap, so this mean is actually correct. Now, if we compare this to the exact solution, it's about, a little less than 21 steps to reach the goal. And there is a standard deviation, of course, because this is a stochastic problem. So, yeah. So this is sort of the range. Now, later on when we evaluate this stuff, like kind of like the plot would like this is a task where the best you can do is is 1. This is also set up differently where I think when they run this, they don't actually give it unlimited steps. Instead, if the agent doesn't find the item within some number of steps, it's just considered a failure. So all these 0 values here are just where it fails and then it resets. I guess they do that just so it runs better. But you do end up with a lot of worthless episodes in this case. Because you kind of have to wait. I mean, to get feedback from this problem, you do have to wait until you collect the item one time. So all the times that you sort of cut off the episode early, it's just wasted time. Whereas, if you let it run, you're going to have to eventually collect the item to get relevant information. But here, the range is sort of 0 to 1, where 1 would mean that this is succeeding every time. And then a lower value is just, the percent of the time that the train policy finds the item within the time limit allotted to it. Here I'm setting it up where it has unlimited time, basically, but what we really care about is the average of how long it takes before it reaches the goal or finds the item. So in the random case, it's pretty bad. We're pretty close to 0 for the average, and the actual number of steps is 3,800 or so. And then the best we can possibly do with and like I know this is guaranteed to be the best because this problem can be solved exactly, is 21 steps, and then the reward per step in that case would be about, oh wait, sorry, this should be 0.048. Let me just fix this. Yeah. So when we look at some plots later, which look, similar to this plot, basically like the high watermark line you could reach is about 0.048. You keep that in mind. And last time I basically just discussed, because this is a tabular problem, you can also apply like these Q-learning techniques. Like earlier in the chapter, it culminates in this DQN, but they also discuss deep Q-learning. There are lots of other versions of this with approximation. There's sort of this whole family of SARSA algorithms where, really, SARSA is the on-policy version of this, where you have to have the next action available to you. Deep Q-learning is sort of, it's not, it's an extension of SARSA, but it's not really it's not an entirely safe technique, because what you're doing is you're calculating something that's off policy, and when you combine off policy with approximation and all this stuff, you can wind up with problems. And we discussed that last time. It's discussed in a lot of detail in the Sutton and Bartow book, but DQN is designed to address some of those problems. But you can also treat any of these approximation techniques like as a tabular problem. Like that's what I showed last time, where we had applied like deep Q-learning, but here there's no deep learning really to it, because I'm just doing here linear approximation, where notice this matrix, which is the parameter matrix that I'm learning in this linear function. So this is like this matrix represents the action value function here. And the reason it's 70 by 4 is because this problem has 70 states to it. So I'm effectively just like, there's no point in doing this, because this is just a worse version of getting the exact solution with a tabular method that you could use. But you can still test these algorithms with this sort of tabular style solution. Like all of these parameters independently represent the action values, which is why now the problems you run into when you use approximation are when you have functions that combine state values together. So you have to somehow, approximate the state space with a function, and the parameters don't just directly store the action values. They rather store, some information about a function that is going to represent the action values. So last time I just sort of did this trivial case, and I wanted to touch briefly on, oh yeah, the other thing. So whatever solution technique you're using, there's this other aspect of these approximation methods, which is not really covered in the book here. They mention it when they show some of the figures. If you actually look at these algorithms they show, like this is the deep Q-learning pseudocode in the book. Now, this target value here, if you see, this uses the reward and then a Q value at st plus 1, right? Now, this st plus 1, this is the part of the algorithm where we use the value function to bootstrap the value at the next state. So like really, to do this properly, we would need to have a target which had the sum of rewards all the way into the future. But we don't have that information when we're running the algorithm. So we sort of have a couple of options, right? One option is to use a Monte Carlo method, which they don't have an example of that here. It is covered in the Sutton and Bartow book. But if you do a Monte Carlo version of this, you have to, run an episode to its completion, and then you have all the reward data, and then you can use the target values where you actually sum the rewards. But that doesn't work that well. You can run into problems with that with approximation. And one of the problems is that if you have an environment where, like, you're going to start with a random behavior. And if you have an environment where random behavior can never solve the problem effectively, then your episode's never going to end. You're never going to get any feedback. Whereas in this case, we start updating our parameters immediately, right? Now, the initial updates are not going to be good because they're not based on anything. We're just bootstrapping off of nothing. But what it can do, especially in a grid, like in a task like this, if you start randomly moving like around the starting state, the parameter updates, if your function is actually capable of solving the problem, what you hope happens is that as you get zero reward around here, like if you're just randomly moving around, the function will it'll change the parameters such that it discourages staying in this region of the state space. So you hope that, like, even though you don't have any feedback about where the goal is, you do have the feedback that you haven't accomplished anything yet. So it'll sort of force the agent into other parts of the state space. And hopefully those immediate updates will accomplish that. Where now, it doesn't always work out that way. Sometimes you do need longer sequences of rewards. But the book example here, this is like, we would call this like a TD0 method, right? Where we're doing the update with as little information as possible, with just a single reward value. Now, if you look at this figure where they sort of evaluate DQN and compare it to everything, they do mention here, where do they mention it? That they're actually using n-step returns. Or perhaps, maybe it's in a later figure. I thought they mentioned it here. Well, it's definitely mentioned in later. Oh, I guess maybe that actually is for one-step returns. I guess they discuss it down here, where they look at sort of the advantages and disadvantages of using different values of n. This is another thing commonly discussed with problems. Like, there's usually some value of n that is ideal for a particular problem, and then where you have this nice balance between the variance and the bias. Like, if you use Monte Carlo returns, where you go all the way to the end, you have the highest variance, but you know that what you're sampling is actually, like, the expected value of that is actually the value you care about. If you start doing anything short of Monte Carlo, you have some bias in your estimate, which is based on your value function is not correct yet. So that bootstrap value you're using is not going to be correct. So they use, a value of n equals 5. Eventually, with some of these later plots, they show, this one they use n equals 5. But if you look at the chapter, like, none of the pseudocode they share in here actually presents an n-step algorithm, and including DQN. And for the other algorithms, one of the reasons for that is that doing like n-step Sarsa is not really that, like, that there's a better way of doing that. And in the Sutton and Bartow book, the way the approach taken to that is with these eligibility traces, which is a technique where you sort of accumulate part of the gradient over time. And then by doing that, you can still run your algorithm like as if it's like a TD0 method where you're updating on every step, but you have a way of incorporating multiple steps of return values and weighting them by different amounts. So the higher the value of lambda is, the closer you are to Monte Carlo returns. And lambda equals 0 is the same as like the one-step method shown in the book. So even for this like tabular style learning, we can see that like the convergence ends up being a lot faster sometimes if you use some value of lambda, which is like using an n-step return. And sometimes like this chart where they show the DQN performance, and later on, sometimes these batch techniques, like DQN is a batch technique because we accumulate this buffer of information and then train on it, sample from it and train, instead of just doing like with the deep Q learning, right? This loss function, we're just calculating it on a single example every time. The idea with DQN is that we now compute the loss function over a batch of data where we've accumulated that. And sometimes like this batch does different things to improve the situation, including, decorrelating the examples so they're not all, states that were visited close together in time. But sometimes you can also achieve this faster convergence by just using like more of an n-step return or like an eligibility trace with a higher value of lambda. Of course, you can also do DQN with n-step returns, and that, maybe you can achieve the best of everything. And that was something, because they don't have pseudocode for that in the book, but when you have DQN, it's not that hard to add n-step returns to it. And that's because we have this replay buffer, right? And the replay buffer is going to have, this stack of previously visited states. And we have all the transitions stored in the replay buffer, including the rewards. Now, when we sample from the replay buffer, and then all we really have to do is change these target values. So instead of the target value just being the reward value for that sample, we can actually look forward in the replay buffer. We can look at like the next n steps in the replay buffer, and we can just calculate that n-step discounted reward. And then we can also see for whatever state we end up in the future in the list of the replay buffer, we can then bootstrap on that state, right? So the target value is going to be this RK plus gamma times RK plus 1 plus gamma squared times RK plus 2 up to whatever n we want. And then the final bootstrap value is just going to have to use the state at k plus n instead of k plus 1. So like the replay buffer kind of gives us an easy way to do that. Of course, you do have to wait till you accumulate enough in the replay buffer where like you kind of have to cut off the end of it, because if you get to the end of the buffer with more recent states, right, you don't actually have the information about all of the n returns into the future. So I did add that to this DQN code. Just see. Okay, so this is like the DQN function I had showed last time. And now there is, oh yeah, I also added double Q learning. That's another extension mentioned in the book where you incorporate this change where instead of just taking the argmax, like the maximum value of the target network, right? Where here we have sort of two sets of parameters. One is our target parameters that we update less frequently. So we use that for the bootstrap values, and we hope that by updating them less frequently, we avoid some of the correlation problems we get where, like ideally this gradient, this loss function shouldn't depend on the parameters. It usually does to some extent, but here, because our target value now, we're using this older set of parameters, it doesn't depend as much on the parameters. So we can, avoid that problem a little bit. But with the double learning, we actually use both networks for the target, where now we use the values from the value network, but to get the argmax, oh no, sorry. We use the values from the target network, but we use the value network to pick the maximizing action that we're using. This avoids, there's this maximization bias problem that can happen sometimes with all versions of Q-learning and SARSA. So this is one way to avoid that. So there's this double learning thing, and then, oh yeah, this n. So here, like the default is n equals 0, which means we just do like the one-step return. And then for every n greater than 0, we do, we add up some of the returns. So really most of what's important here that happens is in this target update, where now if n is larger than 0, we end up adding up the returns for a certain number of steps. Yeah, so here's like, previously this target update didn't use n at all, and by default it would just here, I guess this version of it is probably the most straightforward to see, but yeah, this is the part here where I am, if n equals 0, yeah, if n equals 0, then this loop just doesn't happen, and we just have g equals r, which is the one-step return. But if we have n greater than 0, I just keep adding to g these other discounted rewards to g. So this, and then we just have to keep track also of which state we end up in at the end when we do this. Yeah, this end step. There's a few like annoying details about it. Like if you reach a terminal state before n, then you only should add up the rewards in the sequence that end at that terminal state. Because then if you keep going, you're going to end up in like, it's just going to be a wrong value because the replay buffer is then going to reset with a new episode. And these types of issues always happen with episodic problems. We have to worry about, the end of an episode, and so you have like inconsistent numbers of n. But, we can now combine DQN with n-step returns and see how it impacts. So like this, because if we're not using DQN, like if we're just using one of the techniques that actually can use eligibility traces, we don't have to worry about all this stuff. This use of lambda kind of shortcuts all this need to actually add up the returns. But unfortunately, we can't combine a technique like DQN with eligibility traces, because when we do DQN, we're actually computing the loss of this whole batch of data. And all of, we're going to get a single gradient update from the loss. It's a whole batch. And when we do eligibility traces, we have to actually isolate parts of the gradient and accumulate them. And we're sort of separating out one part of the gradient that doesn't include the loss function with the actual like delta value, which is inside the loss function here. So when we do something like DQN, I think we're kind of stuck with just doing n-step returns the old-fashioned way. But it still works. Here, I'm just showing right here. I'll go down to where I have some of the DQN results. So here, for the case where we're storing all the parameters separately, it's like tabular. There's no real point to doing DQN. Like there's no problem we need to solve when we have that separation of all the values. But if we do something like linear approximation, here we can see these are just different plots of the performance experimenting with, DQN has a lot of hyperparameters. You have to worry about like the buffer size. Luckily, there's just one learning rate we have to worry about. And then these are the different n values where I've just selected a particular batch size and learning rate. And we can see that n equals 0 actually converges the slowest, which makes sense. That's often what we see in problems. And then as we go higher, like n equals 4, we get much faster convergence early on. Sometimes the higher variance then starts hurting you later in the learning curve. So in this case, it looks like n equals 1 might be a nice compromise. It doesn't seem like much. We're actually just adding one more reward value we're just looking one more step in the future. But sometimes that's enough to make a big difference. We can see here also, keep in mind, so the maximum we can do, the exact solution was like 0.048. So here we are doing quite a bit worse than that, but I'll show you, like, this is using a pretty simple linear approximation, which it's kind of hard, it might be hard to believe that it actually succeeds at all in this problem. Here, I also do it here. Yeah, this is just doing it with regular Q-learning. We can see here in this case with, even though lambda equals 0, like this is like the sort of equivalent of this chart in the book where you're just doing like vanilla deep Q-learning. The point is, like, this does much worse than this. You know, this is also showing environment time steps. DQN also does a lot more training updates because it samples from these batches. So what they don't do here, which they do later in the chapter, is show the sort of computational time, like the performance after a certain number of computational steps. Because you don't really care about the environment time steps unless you have a problem where you have a really limited budget here, or this is the slowest part of the process. Oftentimes we can interact with an environment pretty quickly, but then we care about like the actual computational budget we have for the problem. So this might be just doing well over this time because of how much extra computation is done. But I found for this problem, you know, even like you can achieve a similar dramatic improvement in the speed of convergence by just using like a higher value of lambda more. And this is also kind of looking at more data every update. It's not a batch of data, but it is sort of effectively taking into account more of the reward values for a single state. We can see like this is doing pretty well, right? 0.025. It's about like a little more than half of the best performance that we could do. Here, I'm showing this is the exact value function from before, and this is what it learned with this Q-learning. Now, you can actually kind of see the shape of how it solves the problem, because when it, like the policy is based on moving towards higher value. So if you sort of trace the path of wherever you start, moving to a square that has a higher value, that's how you like end up at the goal state. And that it's sort of like a little screwed up in this part. It should continue to get higher as we get right under the goal. But you can sort of see the shape of it. So it's not the exact right shape of the value function, but it's good enough to, you know, solve the problem. And, you know, this is obviously much better than the random performance that we get where, you know, that's like down here. So it's a pretty big improvement. Now, like the linear approximation I'm using is just to give you an idea of how it works. So basically, instead of like having this parameter function like here, all right, this is like the version that's sort of equivalent to tabular learning, where we have like 70 by 4 parameters here. Now, the simplest approximate like linear function you could imagine doing for this, that's not just the tabular version, is saying, well, in this case, we have this grid world state. It just has an X and Y position in the grid. And I know what the range of the grid is, right? Like X goes from 1 to 10, Y goes from 1 to 7. So what this does is it just updates a 2-element vector with a normalized value. Or here I'm just normalizing the values between -1 and 1. Yeah, this is like often what you do when you have, like, it's nicer for the approximation functions to have, you know, a feature vector with a limited range of values for each component. So this, like the feature vector just has 2 values. So when we do linear approximation with this, actually we're only going to have 2 by 4 parameters instead of 7 by 4. And we're still going to have a different function for every action selection. But you can imagine like this, the only thing this function is able to do for each sort of slice of the action space is just draw like a hyperplane through the state space. Because it's doing action value selection, it has more, like, it can actually kind of have 4 different linear functions that it has to work with, but it's still really limited in the shape it can make. Like, this value function is not, you can't represent it with a linear function. And, this is probably the best it can do, this type of thing, right? It's still way more complicated than just a single plane through the state space, where this would all just, like, it would just be like a 2x2 gradient. Here, because you have these overlapping planes, it can form a more complicated shape. So it is able to do pretty well. In fact, doing this with a like nonlinear function approximation, because it probably takes a lot more data to learn. Like, here's an example of a learned value function with, this is the size of the network they use in the book. It's just like 32 by 32 hidden layers. And I have some learning curve data. I didn't spend too much time trying to like optimize this, but it's actually way harder to get the optimization with nonlinear function approximation. I mean, there's just a lot more hyperparameters you have to work with that depend on the architecture. And yeah, you may need a lot more training steps to work. And in this case, I mean, while a nonlinear function could probably get pretty close to this value function, we don't actually need much better than this to do well. I mean, this is already doing quite well for a simple approximation. Okay, so that's, yeah, so DQN, we have, these were the sort of, tabular examples I already showed. Case when you do linear functions, we can see, like, whatever we tweak, all these parameters, we're not really getting any better than we had with just the linear Q-learning without doing all the batch updates. But, it's about the same. Like, if you do enough hyperparameter tuning, like, I'm sure here, if they experimented with different, like, values of n, they could probably get these to converge also, similar to DQN. Of course, I don't know exactly. Oh yeah, I guess this was also using nonlinear approximation. So I would guess that also, because the nonlinear approximation probably needs a lot more training steps to converge. The DQN effectively just does a lot more gradient updates, which is sort of hidden here because we're not showing the computation time. And that's probably one of the reasons, just this number of steps probably isn't enough for the nonlinear function to learn this. Yeah, this is doing, like, here I'm showing my, like, in my case also, when I used a nonlinear function with 32, 2 layers of 32 hidden layers, we can see here, like, this is actually working. I mean, I'm testing a lot of hyperparameters, like with the batch size and the value of n. Here, n of 16. So, like, in order for this to converge within, this is just 100,000 time steps, you need to use, like, these low batch sizes. This is like what you do when you're not doing DQN, right? So clearly, having a larger batch size is really important, right? If we do 2, 4, we're converging pretty slowly. And you don't get much benefit past, like, 16 in this case. They go all the way up to 512 in the book. And then you also get a lot more, even more improvement using a higher value of n here. And then this is, like, sort of the best I could do in the end here. Again, it's about the same as we had in the case, sort of the best case scenario for linear approximation. But the function is much more complicated here. I mean, now we're going to have a 32 by 32 network. Go back to just the actual this with linear. Yeah. So, like, these are the parameters it learned, right? It's just 2 by 4. So this is very little information compared to what we have in the tabular case. So it is pretty, I mean, this particular one didn't converge very well. But if you go back here, right? Like this is the solution I got doing with eligibility traces, this solution. And right, like just this, right, these 8 values are able to practically solve the problem. Something that normally takes, 70 times 4 values to actually represent exactly. But this is our goal when we're using approximation, right? Like in this case, we don't need that many numbers to solve the problem, just 70 times 4. But it could be an infinite number of values for another problem. And what we're trying to get is some extreme compression of the information we need to solve the problem, because that's the only way we're going to be able to solve problems with an enormous or infinite state space. And in this case, we could do a pretty good job with just 8 values in this linear function. I mean, the irony of what they do in the book here and what I do with the nonlinear approximation is that this 32 by 32 neural network, I guess, I thought they mentioned it in the caption here, that that's what they're using. They mention it later, but that's the size of the network they're using. And like that network actually has more parameters than just what you would need to represent this problem exactly, right? So it's really like you're in a regime that doesn't really make any sense practically, but it is a good illustration of how hard it can be to actually get a nonlinear function to converge sometimes, even with a very simple problem like this. And you may need to pull out all the stops with DQN and use that's sort of what I have to do here, is like test out exactly what batch size you need, do higher value of n, and all that. Yeah. Okay. So yeah, DQN is just a way to extend these methods and hopefully take advantage of hardware, really, because when we do this and we create batches, a lot of the hardware we use nowadays is designed to really easily compute these gradients across a large batch. It doesn't even require like writing multi-threaded code, because this is just going to end up being some like matrix multiplication, and all the parallelism is going to happen like in the linear algebra library that we're using, right? We don't have to like actually compute each component of this loss separately. So now when we move on to policy methods, the goal again is going to be to take the basic algorithms and extend them in a way to make them useful, by hopefully getting to a point where we can compute some gradient over a batch, because like doing the batch learning is going to be way more efficient computationally, and it can also help with some of the variance too in the gradient computation, because when we use a larger batch, we don't have this high variance of just looking at one example at a time. So before I move on to the policy gradients, are there any questions about DQN implementation, n step, or this example we're looking at? Okay. So, policy, it turns out when we're using approximation, there are cases where we actually need something that can represent a policy with stochastic elements. So because we don't know the exact state values or state action values like we normally do, there are problems, famous examples you can write down that are also discussed in the Sutton and Bartow book, where the best you can do with an approximate policy is something that incorporates random actions, and not just random like we take each of the actions uniformly randomly, but like specific probabilities of different actions. And when we do policy gradient algorithms, we learn, that's just like illustrating it here, how like you can have like specific probability values. When we do exploration with value functions, all we can really do is just assign some like here, these are just uniform, there's a uniform level of randomness that we can assign to all the actions, and then what's left over is in the preferred action. But we're really just limited to having one preferred action and then some amount of randomness. Whereas here we can have specific probabilities. In order to do that, we need a function that outputs a probability distribution across actions. And often that is done with, it actually probably is a little easier to understand in the Sutton and Bartow book, where really what we're probably going to have is a function, this function h, that outputs values that are going to, you can think of as action preferences, but they could be any value, any real number. So it could be negative. And then we use the softmax function here to convert it into a probability distribution. And yeah, so here, if we're doing linear approximation, this is just, we just have to take, a matrix multiplication of our parameter matrix, or, I mean, this is showing it with a vector, but oftentimes it's done where you just have x of s, the state feature vector, and then you compute all the action preferences together, and then we apply this at the end. So all these algorithms hinge on the policy gradient theorem, which, again, on that slide I showed at the beginning, there's notes about when we went over it. It's covered in chapter 13 of this book, and there's a pretty nice proof of it. But this is the example I mentioned, where this is just one of the toy examples where if your approximation function is restricted, like it is here, the optimal, like the best you can possibly do is a policy that has this specific probability for one of the actions. But the idea behind the policy gradient theorem is that we have some goal, and in this case, the goal is to maximize our performance in the environment. And we have a concept already that captures what we mean by performance, right? This is just the value function of this policy. This is written as for an episodic problem, like we care about the value from the starting state. And this will capture everything important about the environment. So, like, as long as we maximize, and this is the true value function, the value in the starting state, that is the best that we can do. But in this case, now the value function is based on this policy, which depends on these parameters, pi. So we want to know if there's a way to maximize this. And what the policy gradient theorem proves is that there is a way to maximize this using just the policy function itself. As long as we can take samples of the value function. And there's different ways of doing that. But I think what's sort of the most surprising thing about this is that if you imagine, like, we have to be able to take the gradient of this. And this value function, it depends on the parameters, but the parameters also affect the whole behavior of the agent in the environment. So it's going to affect which states are visited when, and like the whole distribution of how the states are visited. And it seems like if we compute this gradient, it's going to include terms that are gradients of things that we don't know about. Like, we don't have information about all of this. And what's proven in here in this box, and I'm not, you can look, there's some videos in the past where we went over this proof and how it works. But we end up with a calculation of the gradient where the only gradient term is the gradient of the policy function, which we have, like we've defined this. And now it appears as though we also need to have the value function. right? Which we don't have, right? This is like the true value function. But we come up with algorithms like the simplest one is reinforce. And you can rewrite this in a way where we actually just need something which is the expected value of this sum. And actually we don't even need this. We can also rewrite this, where you'll often see these terms, this gradient divided by the policy. This is often rewritten as the gradient of the log of the policy, right? Because that is the same as this. When you take the gradient of the log with the chain rule, this goes in the denominator. And you can write this so that actually we just need this gradient. And then we need to calculate the expected value of, like, we need to be able to sample something where this expected value is going to work, right? This is the expected value of the return from this point following the policy. And because reinforce is a Monte Carlo method, we can actually get a sample of this because, right, this is the first algorithm we look at, reinforce. G, right, we just need to sample something where the expected value of this is the true return we would expect from the current policy from the state we're in. And because we go through the whole episode and collect the reward data, we have that, right? So this is like a really pure technique. It doesn't require any bootstrapping. It does require that we actually have a policy that can terminate at the end of an episode, where it's not going to take too long. We saw for the grid world example I showed, it might take a few thousand steps in that case to actually terminate. So this algorithm is also, this should all look about the same as in the other book. We end up rewriting this. Yeah, here they're showing G, they're writing it here as an explicit sum over the rewards. Right here, we have to compute this discounted sum into the future. And here they're actually showing it where you do it, practically you don't recalculate the sum every step. It's better to go to the end of the episode and then, move backwards, where at the very end of the episode, you just have the one reward value and then you can sort of accumulate them through time, going backwards. So there's some modifications you can make to the reinforced algorithm as well. Like normally, the basic version of it, we multiply this gradient times G, where G is the full discounted return, right? But it turns out we can also subtract, or we can add to G any value that doesn't depend on the action itself, like this action that was selected on the step. And one of the best things we could, like, our goal in adding a value to G is to reduce the variance we get with Monte Carlo methods, where, these G values, well, if we average it over all the possible trajectories, we get the right value. But there's a lot of variance. So if we subtract a value from G, like a baseline value, then we can hopefully reduce the variance. And we can really reduce the variance of these updates. Or wait, is it? I guess the variance actually is going to be no, I think yeah, because like over time, if we sample like early G values, yeah, you could just get, yeah, it's actually like the variance of the gradient update itself, not the variance of the expected value, which is going to be the same variance even if we have subtract the baseline. But we're going to attempt to use a baseline, which is an estimate of the state value here. So it's going to sort of center these action values. Like it's a way of not having like large values that are either much greater than 0 or much less than 0. Because now when we subtract this baseline, if it's correct, then all these values in the parenthesis are going to be sort of uniformly distributed around a 0 value. And hopefully then the gradient will move in the correct direction more easily. And usually when we do this with baseline, we just actually use another set of parameters to try to estimate a value function that also is based on parameters. And then we have to also train that value function. Right here, it's just being trained the way we would train the value functions with Monte Carlo, like an actual gradient value function method. Like here, yeah, this is the gradient update that minimizes the value error. So reinforced with baseline, you end up computing this delta value based on, it's sort of a bootstrap estimate, kind of, because we are using an approximation function in here, but this approximation function importantly doesn't depend on the action, which is why it's valid to include this in when we do reinforce with baseline. So here, like, this is the proof in this book about how if we have a baseline value that only depends on the state, it doesn't affect like the final expected gradient update, the final answer, which is what we need for this. So here we can look at how some of these algorithms work in practice. So this is sort of, this problem happens to have an exact solution, right? Which it doesn't need the stochastic policy aspects of policy gradient, but I'm sort of showing the exact optimal policy here, where these are the 4 different actions, and this heat map shows the probability of that action in the particular state. So most of these, the value's yellow, which just means the probability 1. And then the only other probabilities you'll see are like 0.5 or 0.25 here, because this is a problem where you don't need any other probabilities. It's always going to be evenly split between one or more of the available actions. So you can see I'm going to show some of these same heat maps for the approximate policy functions. We can see here, like, it's basically the ideal policy is to go right in most states until you get to this part of the state space, and then you go down along the edge, and then left in this region, or up from down here. But the general idea is to go right, and the functions we're going to learn with approximation are not going to look exactly like this, but they're going to have the same general structure. So here's an example of doing reinforce with the linear approximation I showed, where we just have the two values in the feature vector. So really simple linear approximation. So this is just vanilla reinforce without a baseline value. We can see also, because without a baseline, this is a more unstable method, these learning rates are really small here. But this is still like doing okay. Like this, remember, before we saw with linear approximation, we got up to like 0.02 or 0.025. So this is worse than that, but it's still, these are the statistics for this, one of the policies I trained, but 38 steps. Remember, the optimal is like 21. So it's not too bad compared to the optimal. And then this is showing it with baseline. So now there's 2 different learning rates here, right? Because we also need a learning rate to update the value function that we're using for the baseline calculation. And we can see here now it's approaching the performance we had from the value methods, right? Just adding that baseline value. I mean, you have to tweak the parameters a little bit. And this is one of the learned examples. If I repeat this, the values will look a little different. But we can see the sort of structure is similar, where we go right in most cases. Here's the exact one where, the exact solution involves going right much more often than this does. But you can see the sort of right, down, left structure of the solution. Again, but each one of these is sort of is just a hyperplane, like the way the linear approximation works. We're sort of stuck with planes. So this is a case where actually the type of linear approximation is probably, it might be hurting it in the policy gradient case. It might, this would definitely benefit from a more complex function approximator. Because, right, for each of these probability distributions you want, you need, clearly, like, these shapes are not hyperplanes here. Okay, so that's, the reinforced algorithm. Now, this method, because we have to finish an episode, could be a little impractical. What we introduce later are these actor-critic methods. Now, in the Sutton and Bartow book, the actor-critic method is pretty easy to understand if we compare it to the reinforced method, or reinforced with baseline, right? So reinforced with baseline, we have this gradient update, right? Where we have this delta value, and the delta value depends on some sample of the return, and then this baseline estimate that we currently have. Now, we do actor-critic methods. All we're doing, the only difference is that this delta value now is being computed like when we do the TD methods, or like the deep Q-learning method, right? Where we're just bootstrapping off a single reward value. In the reinforced method, instead of this R plus gamma V hat, we have the reward sum to the end of the episode. And all of the justification of how these gradients work is the same. Like, this gradient update looks the same as before. This one is also the same. It's just that the delta value is now different. There is this small matter of this I, which actually is updates throughout an episode. If gamma is 1, undiscounted, it doesn't affect anything. This I is actually omitted from this book. If we go to the actor-critic algorithm, they have, this is like the one-step actor-critic method from the Sutton and Bartow book. It's just that they introduced this advantage term, where here the advantage is just really the delta value from here, right? Where we have the target value minus the state value estimate. But, the way they introduce it here, they kind of imply it's like sort of a different thing using this advantage function. But really, it's just the same concept that we have with reinforce with baseline. It's just that we replace the Monte Carlo sum of all the rewards with this bootstrap estimate here, this R plus gamma V. And here you can see this loss function they have here with, right? I mean, you have to take the gradient of this loss function. So we have the gradient of the log of the policy, same we have here. And then this delta doesn't depend on these parameters, so it just comes out of, like, when we have the gradient of advantage, right? It's just going to be a multiplication on the outside of the gradient. We can take this because it doesn't depend on the parameters phi. But notice here, there's this I value is missing. So I don't know if I believe, like, it is sort of a minor mistake in the algorithm, because to be strictly correct, you are supposed to keep track of this for discounted problems. But, it doesn't make too much of a difference. Again, in the Sutton and Bartow book, when we introduce like n-step versions of policy gradient, they just do it with eligibility traces, which is this way of accumulating gradient values. Like here, we can see that we still compute these gradients, but instead of just using them directly, we instead sort of take these decaying sums of them we're accumulating, and then the structure of the gradient update with this delta allows us to compute this single gradient update that incorporates a lot of different steps into the past without doing explicit n-step returns. This is really convenient again, because we don't have to worry about keeping track of what n we're on and where we should terminate the sum. So you can always do this with just regular actor-critic methods. And I show it, like here I'm just showing the reinforce method. Later on, oh yeah, this is with, yeah, so this is with eligibility traces. I didn't optimize over all of it, but just by changing these values of lambda, yeah, like here's a calculation I did where these are the two, here we have two different values of lambda, because, you know, two different sets of parameters. But these values of lambda are pretty high values, indicating that I'm incorporating, I'm like effectively using more n steps in the calculation. Yeah, this policy actually is pretty successful. It was learned. Grid world. Now I'm not sure what, oh yeah, so this was, yeah, doing the eligibility traces with a linear function approximation, yeah. So yeah, using values of lambda much greater than 0. And this ended up working pretty well, right? Like mean number of steps is 42, right? The optimal, so this is like twice as bad as the optimal, which is about like the best we were doing with linear approximation. And then this is the policy. We could see the same shape where the right action happens up here, and then, you know, the left action once we get past this point here. Yeah, so just like with the value methods, this eligibility trace method, unfortunately, kind of prevents us from computing gradients in a batch, because we have to like have just this part of the gradient right here. Notice this is the gradient of the natural log of the policy function, and we're actually doing something with it. We're adding it with some decay over time. Whereas here, to do this update, like this, we have a loss function, and we have the gradient of the loss function. It's not like here, there's this other term that we're multiplying by, and this term is going to actually vary. Like if we have a batch of these things, a batch of states, this term is going to vary, be multiplied separately for each state action pair that we have in here. So if we do something that involves batches, we have to sort of forego eligibility traces again. But there is an idea of doing batches. And I'm going to, yeah, here they also mention this PPO algorithm. PPO is just, it's the same as the actor-critic algorithm, but it just sort of constrains the gradients so that we don't move the policy too much on a given step. We keep it, you know, close to the original policy. And they have this chart here of performance of using reinforce, actor-critic, and this here, like reinforce performs the worst. You know, they don't show reinforce. I don't know if this is reinforced with baseline, but I mean, reinforced with baseline performs a lot better. And then also in practice, using different values of lambda will also achieve this much better performance, right? Where like these algorithms here are just like inherently one-step algorithms. I mean, here they show they do it with an n of 5 without using eligibility traces. But, you know, I would say like if you're going to incorporate n-step returns in these sort of simple algorithms, it is probably better to do it with this approach than to, you know, use an explicit value of n. Like the calculation is just way messier with n, but of course doing this does require you can compute these gradients individually before, you know, running them through the loss function. But the idea of doing policy gradient in batches is actually, instead of having a replay buffer where we just sample a batch from the replay buffer, we instead have parallel environments that we're running. It doesn't even really have to be on multiple threads unless these are really slow steps. If the environment step is fast, you can just keep track of different environments. So each environment will have its own state and accumulate its own reward and transition. So we just run all this in parallel. And we have the rewards in parallel. Then every time these environments all complete a step, we assemble all of the data, the reward data, and the transition state. And then we compute the policy gradient on that batch, where the batch size is the number of separate environments that we have. And that is what's being shown here, where here now we have two gradient updates. One is the value function update, which is sort of the same when we have a replay buffer. It's just that now this batch is not over selections from the replay buffer. Instead, it is over the k environments that we have. And then we have this batch loss function, where now we have this advantage value, which is just the delta value, right, per environment, and then the log of the policy function per environment. And now in order to do this algorithm, we're actually going to compute like the full gradient of the loss across the whole batch, right? We're not going to be like separating the gradient terms. So this also, they don't show like the end step version of this. I think it is practically a lot messier to write. So in here, I have added a version of this actor-critic algorithm, a synchronous version of it, where you specify the number of environments. Now, it happens to not, it depends on how the environment works. You could easily run this loop in parallel where it goes through the environment. This is the part of the algorithm where it gets the transition for all of the different states. And then it keeps track of the rewards and everything. Yeah, and then when you do all these updates, like when you update the state values to get the target values, and you update the gradient, this is all happening as like a batch operation, taking advantage of the hardware you have, which in practice it can be a lot faster, especially if you have GPUs. You can assemble really large batches of data, and like this part where we just do the transition might be a very quick step. I mean, just assembling this data, right? Usually the gradient update is what's going to be the slow part of the algorithm. So this, it's not really important that this happens in parallel. It's important that this happens as a batch step where we wait for all these to finish and then we assemble those transitions together. So I was experimenting with this, but with this particular problem with policy gradient, I believe what I found was that the actor-critic method, which doesn't use like what's shown in the book here, right? This is just a one-step method where there's just one reward value. These advantage values are being calculated like this, right? We're not using n-step returns. And on this type of grid world environment with policy gradient, it kind of like, it has a very hard time learning anything unless you have some like number of n-step returns. So my version of this, like the successful examples I showed like here, right? This is using either reinforce or actor-critic with eligibility traces where I am using like effectively higher values of n in the returns. But if you just try to use like one step actor-critic, like I think I tested here on this example. Yeah, okay, this is, or maybe, well, when I tested like one-step actor-critic, it really did not have much success learning. So it's a little hard, at least for this example. Maybe next time I'll have it. If you look at this over different values of lambda, it's just, if lambda equals 0, it doesn't do very well. So in the book, they picked a value of n. Here n equals 10. I think it's a little slightly bigger environment. They don't show these charts over different different values of n to see. I guess they just sort of probably optimize this ahead of time. But this is just showing the performance both as a function of the environment steps, but also now in terms of training time. Because obviously, if we add more environments, we have more data, we would expect it to train faster as a function of environment steps. Although here, actually, we could see it's still, I mean, this 64 environments is actually training slower. So if the batch size is too big, yeah, I don't know, like just like training, supervised learning, sometimes like if the batch size is too big, it actually slows down learning. But, you know, this is just in terms of environment steps. The training time itself, we can see that the best is around n equals 16 for the number of environments. Just because, yeah, it's a nice compromise between the batch size being small enough where the updates are better. Like it's not washed out so much like we get with really big batches. And then, you know, we get a lot of parallel speed up. They do mention here one of the reasons they mention why having large values of k, that the threads have to wait for each other. I mean, I guess in theory that's true. Like if you're doing this, you have to wait for these all to sync up. But I would argue most of the time when we're solving hard problems, the gradient update is the slowest part. Like this waiting time here is going to be almost nothing. I mean, in my version of the algorithm, I don't even have that step happening in parallel. Like, so of course, all the different environments have to wait for each other. But it doesn't really matter because we're just trying to assemble this big batch set of data to do the gradient update with. So I think more the issue with a larger batch size is just that the gradient updates themselves don't work as well. Like, you know, when you do stochastic gradient descent, sometimes there is an optimal batch size that you have. So I would guess that's more of an issue. But again, I don't know how this was running. Like the problem they're using it on is so simple. I can't imagine like the waiting for the other environments to finish is actually one of the problems here. But yeah, in order to really evaluate this, I would have to have probably an n-step version of this algorithm test, and that just, it introduces a lot of annoying complications in what you have to keep track of, because like we have this, the main problem is you have these threads and we're synchronizing these batches of data. If we have n-step returns, there are times when like one episode terminates and other episodes haven't terminated, right? Because like the example here is an episodic problem. And then we have like one part of the batch where we have n up to a certain value and it's all in sync. And then other parts of the batch where now we've started a new episode and we don't really want to compute that return yet because we want to wait for the n steps to occur first. And like it's already kind of a pain to deal with n-step returns and normal algorithms, and then having the synchronization on top of it makes it really annoying. If you do it asynchronously, like is shown here, where we just have these computations, like these gradient computations are now happening. Like you could do this with any algorithm, right? Where you just, you compute the gradient updates you want in parallel environments with individual threads. And then when you get a gradient update, when it's ready, you send it to update the agent policy. This Um, you can manage each thread however you want with the end step returns. Nothing has to be synchronized. But this is not going to be nearly as effective as the synchronous one, because the main benefit you get from the synchronous environment is the ability to compute the gradient itself as a batch. Like that's what, modern hardware is really designed to do. So, this we're just, we can compute this stuff on individual threads, but, the modern hardware now is good enough that like even a single thread benefits from batching, because like even a single thread can do these linear algebra operations with a batch of data much faster than just a sequence of individual updates. So yeah, I think this is probably the most promising version of this, but really to make it useful, like for most problems, you do need probably an n step version of this instead of just the TD0 version they show here. And I think there's a lot of messy implementation details which they don't go into. I mean, it's probably why they don't have pseudocode for it, just because it's practically kind of annoying to deal with. It may look pretty messy. Yeah. There is also, at the very end of the chapter, there's this comment about, like here we're just looking at functions that depend on the state, right? When we move on in the next chapter to multi-agent problems, we generally need to look at this history of observations, where the observations include the past states, but also maybe behavior of other agents in the problem. And this can be hard to deal with function approximation because the length of the history changes. Now, you could just have a maximum history length you look at, like the last 5 steps, and you pad it with zeros for the time where you haven't gotten to that history yet. And you just like deal with limited history, which might be a good idea. The other solution they mention here is the idea of using LSTMs, which is a form of neural network that has an internal memory. So you can pass it a sequence of input data, and it will update its internal state, and it can deal with, in theory, like an unlimited history. That's one approach. I mean, LSTMs are also hard to deal with. They are not the most popular architecture right now. Like transformers are much more popular. Transformers, however, do have like a fixed length. And really using a transformer or just like a simple perceptron is going to sort of have the same issue here. Now, with a transformer, we may be able to accommodate a longer history, but we're still going to have some fixed history length that we define. And then we have to sort of zero out the data for the part of the history we don't have yet. Kind of like when you're using a transformer model, right? And you ask for a response, like a lot of the context window is just empty. And the model has a way of dealing with that. And it's the same thing we would have here with a history, where just a lot of the history might be blank, and we just, have some maximum cap on the history that we deal with. But, for this history of observations is only something we need to deal with for the multi-agent problem, which is covered in chapter 9. Yeah, so I think that concludes what's in chapter 8. Yeah, the main extension of what we had from the Sutton and Bartow material is just the batch learning. So the batches we get with DQN, and then the batches we get with synchronous type actor-critic algorithms. And, often you can get better performance using that. But, you have to do some kind of evaluation like this where you look at what's important to you, like the training time, or maybe you have a limited budget of how many environment steps you can deal with. And if your environment steps are really what is limited, probably to get the best bang for your buck for each individual step, where you can't have have it in parallel is to do something like using eligibility traces with like actor-critic, because this is probably like the most efficient way to use like a single interaction with the environment to its maximum effect. But if we can run parallel environments, it's great. We can experiment with seeing if we can get, faster training time total. So are there any remaining questions about policy gradient methods, or how, how the synchronization works? So yeah, the next chapter is actually, I mean, the way they wrote this book, these are very large chapters, but I think this is actually the last chapter of the book. The rest is just like appendices and, or no, actually no, there is a chapter 10, sorry, I think, but chapter 10 is just sort of coding, yeah, different like coding examples. And then there's a chapter on environments, which is not really, yeah, the actual like covering of algorithms. But like the last chapter that actually covers algorithms is this giant chapter 9, which has all these different deep learning approaches for multi-agent games. So yeah, this, I don't know, I have to start looking at it, but this is like kind of effectively like 5 different chapters just because of how many different sections it has. But this is what we'll start looking at next time. Yeah. Well, if there's no other questions, yeah, we'll stop for now. But yeah, thanks for coming, everyone. You can always write a message in the like discussion section of the meetup, or someplace else, or post a GitHub issue if you're looking at the code and have a question about how it works. Yeah, we'll see everyone next time.